Welcome everyone at the first PyData talk of today. Our first speaker will be Vera van den Bogaart. She is a data scientist and consultant at Pipple. Her talk will be about the LIME framework, which is a model-agnostic framework for explainable AI. So please give her a big round of applause.
Thanks, guys. Well, hello everyone. I don't know, is the microphone working perfectly? And welcome everyone to the first talk after the keynote speaker this morning. And my talk is on XAI in the limelight. This is a limelight, by the way, and I noticed in my office that not everyone was sure on what a limelight actually is. And first I want to talk about the black box. So I think everyone here who's familiar with machine learning models knows the concept of black box. So you put your data into your model, you obtain your output, and you might be very happy or not happy with your output. There's quite some metrics to measure whether your model does a good job or not. But in fact, this box stays closed. You don't know what happens inside of the machine learning model. And over the years, the machine learning models have evolved. They've become more complex, bigger, maybe more efficient, hopefully better. But the one thing that stayed the same for a long time was that this box, the black box, stayed closed. But what if I tell you that the black box can be opened? And one of the ways to do so is by using LIME. So, nice to meet all of you. My name is Sanne van den Bogaart. And I have a background in econometrics and operations research. I studied that at the University of Maastricht. And during my master thesis, I stumbled upon Pipple, and after graduating there, I stayed there working as a data scientist. And I've been there now for almost 3 years. I've been doing lots of projects in different sectors. So I've worked for a bank, car manufacturer, but also a hospital. And actually, no matter the type of project, no matter the company we did the project for, the one thing that was always very important was explainability. Everyone in any way asked for this. And by explainability and explainable AI, what do I exactly mean with this? And why would you want to have it? So there's 3 main reasons to want to have explainability into your machine learning model. And the first one, not even being something you would want, but actually something you need. You're obliged to have it because of the EU AI Act. So this is a legal requirement that has come into play. It's either coming into play shortly and throughout the next couple of years. But this year, I think it was May this year, the EU finally agreed upon this act. And it's here to make machine learning and artificial intelligence safer for all its inhabitants. And depending on the risk level of your model, you would actually need to have a certain level of explainability. Secondly, your user might wish for this explainability. And the user might be your colleague, your manager, the client you work for, or even the public. But in order to really trust the outcome of your model, they might require to have some explainability. Lastly, explainability is enormously helpful with improving your model. Because in case you get a certain outcome of your model, you have a certain metric, it works relatively well, or maybe not very well. But in case you do know why it makes a certain prediction and you exactly know why it makes a choice, you can also improve the model. Because maybe even you get a very good score for your model, but then you see that the feature it makes a choice on actually doesn't make sense at all if you just think about your own expert knowledge on it. That's very important information to have. So now we know why we want to have explainability. Then what types of explainability are there? Well, the first one is global explainability, and this explains the model in general. So to give an example, I took the very well-known data set of the passengers of the Titanic, and which ones of them survived, which did not, and the characteristics of the people. Now, if you want to consider the global explainability of this model, we see that in general, whether you would survive or not, it's the characteristics which are very important are the fare, whether you're a male or female, and your age. But this is then global explainability. On the other hand, we have local explainability, and this does not explain the model in general, Rather, it explains one single instance of the model, and it really looks at how the model reasoned and which features were important for this specific outcome of the model. And as an example here, instead of looking at all of the passengers of the Titanic data set, I considered just one. I recreated the character of Rose from the movie. And well, the movie, she survived, but also our model predicts her to survive. And what then is are her important features for her to survive? Well, the model tells me basically the fact that she's a female gives her a very high chance of survival, but also the class she was in and the fare she paid. And this makes a difference between global and local. And now it's time to finally introduce the package that this talk is all about. So this talk is all about Lime. And the name of Lime was not created because the people who created it really loves limes. No, Lime actually is an abbreviation. And in fact, the abbreviation already tells you everything there is to the package. So the L is for local. So we just saw global and local explainability. Lime is especially for the local explainability. The I is for interpretable, which means that it gives an explanation that is as easy enough for a human to be able to interpret the explanation. The M is for model-agnostic. This is a really cool feature, I think, meaning that the package works on any type of model. So regardless of your machine learning model, you can use Lime. This, however, does not mean that it works on any type of data, which is an important thing to notice. And I will get to which types of data it supports in a couple of minutes. And lastly, we have the E for explanation. So Lime is a local, interpretable, model-agnostic explanation. But okay, that sounds amazing and very cool that it can do so. And I want to tell you shortly how it does so. I'm not going to go really deeply into the math behind it, but I think it's important to have at least an idea of how it can give you this explanation. So what it does on the left side, we have the full real model, which is a very complex nonlinear model in this case. And let's say we want to have an explanation on one of our instances, and this instance is the big red plus, which you see on the left side. Now, in order to obtain an explanation for this one big red plus, we zoom into the phonicity of this big red plus. So we go from global to local. And there we see that we have a lot of instances around it. And these instances are created by the model. So they're perturbations, they're slight differences of your instance you want to explain. And then you look at these slight differences and you see what the outcome of the model will be there. So there you see, okay, if you slightly change one of the features, it suddenly gets another prediction than it got before. And you're able to train a simple, very simple linear model in this local environment. And this way it can give you its predictions. And now on to the Python framework where we're all here today. Lime is an open source package, so you can literally simply install it by using the pip install lime. And as I told you before, it doesn't support all data types. It does support tabular data, textual data, and image data. And I will give an example of all of these three in a minute. But the thing you will see, and I almost hope in the end of the third data type, you feel like, oh, I've already seen this, it becomes repetitive. Because Lime simply has one framework, and it works the same for all different data types, which makes it very easy to use. And this framework consists of 3 steps. So firstly, you initialize your Lime explainer, and you initialize it on your training data. Secondly, you use this initialized Lime explainer to create an explanation of a single instance. And once you've got this explanation, you can simply show it. And that's the part where you're most interested in, because it gives you the explanation you want. So, coming back to the 3 different data types we saw before. Let's first take a look at tabular data. So, to give an example here, I consider the data set on the NBA, which is the American Basketball League. And we've got a tabular data set in which we have the characteristics of all of the players. We have our target variable, well, whether a basketball player is a all-star or not an all-star. And we train a random forest on it to make this prediction. And now I have a new player. I make the model predict whether this player is an all-star or not, and it gives me insert and output. And I want to know why. What features of this player are really important for it to be an all-star or not? Well, to do so, I'm going to go through the framework I just explained you. By first initializing our Lime explainer, which in this case is a Lime tabular explainer. Secondly, we create this explanation for this new player. And lastly, we output it. And the output is probably also where you're all most interested for. And it looks like this in case of tabular data. So we see here our model has a 72% for this particular player to be an all-star. And why? Well, it predicts so because of its very high minutes played, a lot of rebounds, turnovers, and steals. But it also tells you why it predicts it to be not an all-star, which is in this case his low number of blocks, points, and assists. So then going from the tabular data towards textual data, yeah, I could not do differently than take an example of the place where we're here today. So in the PSV stadium, and as was already mentioned by Koen before, PSV became the champion of the Netherlands this year. So I took this newspaper article and I trained a model to predict which class this newspaper article is in. Well, I hope it predicts sports, and it does so, we will see. But then I'm curious, what words does it pick on? What words make it think it is actually a newspaper article on sports? In order to do so, I used the same framework. So I initialized my Lime explainer, and this time it was a textual explainer instead of a tabular explainer. Secondly, I created a single explanation for this newspaper article, and then I showed the output. And the output looks like this. So what were the words that made it think it is a sports article? Well, it's because of champion, victory, team, and ball. And the two words that it picked upon which make it not think it's sports are Rotterdam and thanks. So I hope there's not too many Rotterdam fans in here. But apparently the model does not consider your city to be a sports city. So then going from text data to the one I was personally most surprised, but pleasantly surprised about, which is the explanation for the image data. Because when image data in mostly neural networks are used, and I already always was taught in university, like a neural network is a black box. It was kind of like 1 + 1 is 2, so there's no way of you to finding out what happens there. And I kind of got used to this fact, and I also didn't think about it anymore. Until I got interested in explainable AI, and I figured that there are ways to explain your neural network, and one of them is by Lime. And in order to do so, I took an image of myself on a bike, and I was quite curious what my neural network would predict this to be, what's happening on this picture. And it thought I was on a unicycle. I mean, it's not that far off. It is a bike, but not exactly the same. So let's say what part of the image made it think I am on a unicycle. So after creating a certain neural network, again, and I hope by this time you feel like, yeah, I know this framework, because that's how easy it is. Again, we initialize our Lime explainer, which in this time is a Lime image explainer. We create the explanation, and now the visualization part is a bit different than the other times because of you using a image. So actually below this, there was another part with my matplotlib by creating the output you will see in a second. But the idea of it is exactly the same. Now, why does it think I'm on a unicycle? Well, it gives me the green areas of which were most informative for its decision. And some of them make sense. I mean, the bike itself is on it. However, also there's some part on the left side of my head that apparently makes it think I'm on a unicycle. I have no idea why. But the interesting thing on this does not mean that Lime does not work well. It just gives me an insight of my wrong prediction of the model. So apparently it sees that the trees over there give it some information on the unicycle. I don't know why, but it does make me think like, okay, this model is not good enough yet. Let's retrain it or use more training data or whatever way you want to improve your model. But it was very cool to me that I finally got some insights in the areas of an image that were important for your model. And now this might come as a bit of a surprise to you because I've said, I think already 3 times, like it supports 3 different data types, the 3 different data types we just saw. But I do have an extension into time series, which would be a 4th data type. And the reason I've only been talking about 3 data types the whole time is because there's 3 data types which have built-in support by Lime. However, there are some people on GitHub with open source repositories who created an extension of the Lime package into time series. And it was really cool, so I want to show you this, not only because of the interesting parts of this extension, but also just to have you consider like, okay, in case I found a certain package, it can do this, maybe look a bit further. There might be more to it and go on open source and see what's there. Yeah, so as I already said, there is no built-in support. However, someone created the repo Lime for time series. It is a shame he didn't call it Lime series, to be honest, but it is very cool. Oh, there we go. And the example used was on ECGs, which are short movies of a heart. And it gives you the electrical activity of the heart. And it then is a very short time series of this electrical pulse. And there's basically 4 categories it can fall on. And I'm not a medic, and I think most of you are neither, so sorry for the pronunciation. But the 4 classes it falls into could either be the blue line, which is a ventricular tachycardia, the green line, the atrial fibrillation, the black line, which would be a heart attack, and the red line, a normal sinus rhythm, which you probably would prefer. Now let's see if we have an ECG of a new patient, and it makes a certain prediction. Now, what we want Lime to do would be to tell us which part of the time series, so which part of the ECG, was most informative in predicting its class. So what we see here in the upper image is the original ECG of this new patient, and it predicts it to be in the first class, the ventricular tachycardia. But why does it do so? And I hope it's, you can slightly see it. And why it predicts it to be in this class is mainly because of the yellow highlighted parts of the time series. So you might wonder, why is there just 5 of them? Well, the 5 is just a parameter. So in case you're wondering what are the 10 most important ones or just the 2 most important ones, you can adjust that yourself, obviously. However, in this case, we see the part of the time series being most informative. And this was really cool because also a time series is a data type that sometimes doesn't really get the... Sometimes people just accept like, oh, we cannot explain this, but that's not true. And this already brings me to the conclusion of today. So I really want to ask you to make your project sublime, shed your limelight on XAI with Lime. And why? Well, first of all, I hope I convinced you that there's really valuable insights to obtain from Lime. Secondly, it is model agnostic, which is a cool feature because considering you're using a certain machine learning type model, you do not need to search for which type of explainable AI to use. No, if you want to have a local explanation, you can use Lime. And lastly, it's very easy to use. I hope you remember the framework, and it is really easy. So please all use it. And thanks.
Thank you, Sanne. Are there any questions from the audience? Maybe down in the back. Can you?
These examples were all in classification problems. Does Lime cover things like scoring and ranking or recommendations and things like other outputs?
It does indeed also accept other type of outputs, so it can also do with a regression or whatever. What type of models would you use with, for example, your ranking? Would that also be in a regression form, or what form would you put it in?
I think we're currently using a k-nearest neighbors type of model, where you get some sort of a user profile, you put it into the model, you find different users that have similar profile, and then from that profile you go on. Now, k-nearest neighbors is pretty explainable in itself, I guess, but going more complex models in there.
I haven't used that myself, so I can't promise anything to you. However, it would be interesting to take a look into it, but I'm not quite sure. Sorry.
Okay, and there was one more question in the back.
Hello, thanks for the talk. Yeah, so I was wondering, so you're trying to look for local explanations, right? And so it matters where, so the approximation, making the approximation matters. So you can't use this on all use cases, right? So how do you determine when it's appropriate to use Lime and do a local approximation and have that generate a explanation that is valid and usable? And when do you look at a model and say, no, this is not an appropriate use case?
So do you mean like whether you would prefer to have a global explanation, or is that not what you're hinting at?
Well, not ever. So to make a local explanation, you need to do a local approximation of the model that you're evaluating, right? So you showed that diagram with the nonlinear model, and then you zoom in. So the zoom needs to reflect your use case, right? Yeah. So how do you determine whether the zoom is appropriate? How do you know whether you're evaluating your model around a point that is valid? Okay, so when do you use the tool, basically? And when how is your process for determining whether you use the tool or not, based on that?
Yeah, thanks. I see what you're hinting at now. Because that's indeed something that Shep, for example, as another XAI package, does differently. And also when comparing those, people often say Lime is more interpretable, but Shep might be more accurate. So I think that's more the area you're indeed looking into. The thing is, you should never forget like your own expertise. So even when Lime gives you a certain output and indeed you feel like this doesn't make sense, might be because of the case you're describing. For me, in my work, I often work in fields where I'm the machine learning expert, but not the field expert. So often, when local explainability is required, I do use Lime, but I always check it with the experts whether it makes sense to, in that case, know that. I don't do a certain test or something before using Lime.
Right. Yeah. All right. Thanks.
Other questions?
Hi, thanks, Sanne. You mentioned SHAP earlier, which of course is a very popular framework, and one of the things that we struggle with, especially with batch inference, is how slow SHAP can be, especially for the kernel explainer. Do you know how Lime compares to that, and how it tries to optimize for speed, perhaps?
Yeah, so I didn't try it myself, but I read online that Lime is known to be much faster than Shep, because Shep indeed one of its pitfalls is the speed. So I believe Lime is faster, but I can give you an approximation, obviously, of how much faster. But it would be worth it if you want to consider local, because that's also a big difference, obviously, with Shep and Lime. Shep can consider global explanations. But if you're interested in your local explanation, it will be worth it, I guess, trying Lime.
Okay. Thank you.
Thank you for the talk. Do you have any tips on how to explain the results of the Lime to the subject matter experts?
I think you asked, so in case like the explanations that Lime give is not enough, is that your question? Because the thing is, it is built to be interpretable in a way that, for example, like with the, kind of all of the examples, I guess, it really highlights the most important features, and normally those features should have been chosen in a way that they are understandable for your expert. Otherwise, maybe you have a different problem of having features which don't mean anything. But in case you have informative, or not necessarily informative, but features of which you know the meaning, I think Lime will already do the trick for you, because it will give you exactly which feature was important. But I'm not sure if I'm now touching upon your exact question. Yeah? Okay.
Thank you very much for your presentation. I was wondering, did I hear you correctly when you said that when zooming in, it makes perturbations of the data points?
Yeah, exactly.
Can you somehow specify what kind of perturbations are valid within your data space? For example, say you have a medical data set and you have different types of people with their sex and their type of cancer. You wouldn't want to have a male with testicular cancer be perturbated into a female with testicular cancer, right? Because that's just an invalid data point. It would never occur. So is there somehow a way to specify what type of perturbations are valid within your data space?
Not that I know of, but normally you would think, even indeed, if it makes such a thing which cannot happen, then you also hope your prediction to be, you hope that it doesn't predict for it to have this type of cancer. So then maybe it will give you the feature of male being important.
No, but for example, this could both be features, right? Type of cancer and sex could both be features. So if you then perturbate your features into an invalid feature space.
Okay, so it's not the target.
No, so your target could be whether they die or not in the hospital, for example, right?
Yeah.
Very gruesome example, but you know.
Good question. Not sure about that. It's at least not one of the things. Well, I'm pretty sure if you go deeper into the package, you might at least find the answer, but I'm not quite sure if it's possible. It's not one of the first things, like one of the easiest parameters to adjust.
All right.
So I'm not sure.
I'll check it out.
Yeah.
Thank you for your talk. Do you have any recommendations how to structure the exploration of these kind of local points that you want to look at? I'm wondering, like, do you focus on the higher error ones, or do you also look at the kind of normal points to make sure that the model is also looking at like the right features? Do you have any kind of a structure approach to that?
That would also something I would need talk to the expert about. So it might be good to check certain cases they're very sure of, just to see whether the model makes the same prediction as they would do with their expertise. On the other hand, it would also be informative to look at more of the edge cases, so the things they are not sure about. So I guess what would be best is to make like a subset and maybe have it made by an expert or by your own expert knowledge, and indeed consider all of the cases in this subset. There's no rules to it, but really depends on what use case you're in at the moment.
Thank you very much for your presentation. I would like to ask if Lime supports any kind of like accuracy estimation, like when you have like enter some data in the model and we have the test data, does Lime support us to receive an accuracy score or a mean squared error score?
No, it does not, because it really only looks at the explanation of just one instance, so it doesn't consider all of your test set or something.
But it makes sense, but like maybe just some difference between the thing that should have happened and what happened.
Can you maybe
Like
Try to
when
explain again.
in the bike example, there were a score of bike and the score of other things, but maybe in like the normal situation, the bike is 0.15 and we had a score of 0.84. Like, will it give an error rate of that difference? It should be something like maybe in that case 400%, but does it give us that percentage?
Well, the thing is, your model is already trained before using Lime, so I think that's the moment you would look at this score,
Yeah, what?
and then Lime is used afterwards, so Lime does not consider this again.
Okay. So no score is okay. So we can make it manually maybe. Thank you.
Okay.
Can I ask a question as well? Yeah. I want to say for image and for time series, I usually use saliency maps. How does this compare to saliency maps in the way it shows the difference between the input and the output?
Can you ask it again, please?
Saliency maps is a technique that is very popular to see how the input features are represented in the output for especially neural networks. How does this compare to those type of techniques that are like the standard way to see neural networks?
Good question. Haven't tried that on this example, so I not quite sure. Sorry.
Okay. Can you pass it?
Yeah, thank you for your talk. So I think sometimes Lime can give nonsensical output where some binary variable has some value and you would expect it to have a positive contribution to a probability, but has a negative contribution. But this can be due to interaction effects as well, right? So can you also check if variables interact with each other to produce some output?
As far as I know, that's not integrated into the package now.
Thank you, Sanne. Okay, so these were the last questions. There will now be a 10 to 15 minute break, and then we will continue with the next talk.